Let's discuss chapter number 6, efficiency and heating of machines. This is a pretty short chapter and pretty easy to understand if you read it. So I'm just going to make one video and go over each section instead of making multiple videos for different sections. So let's start with section number 1. What are different types of losses in a machine? So there are two major losses. There are mechanical losses and there are electrical losses. Mechanical losses are due to friction. Of course, machines have moving parts. Armature is moving, rotating. So there is friction. And there are losses which are called windage losses. Windage losses are also friction, but they are due to the cooling fans, because many times you have cooling fans that are removing heat from motors and generators, and because of their wind which is blowing to armature, which is a moving part, it produces friction which is called windage friction or just windage losses. So basically the mechanical losses are due to frictional losses where moving parts are rubbing against each other, and windage frictional losses are just windage losses. Electrical losses are divided into three parts. You have basic conductor losses. Anytime current flows through a conductor, of course there are losses, heating losses, which we also called I square R losses. So conductor losses are I square R losses. You have brush losses. In generator motors there is carbon brushes, and many times you have a voltage drop at the contact of the carbon brush where it has the contact with the commutator. Especially if the brush gets old, or if you have armature reaction and your neutral zone gets shifted, then you have a sparking at the brushes. So if the brush gets old, it does not have proper contact with the armature, or if there is armature reaction, then those losses are substantial. Other than that, those losses are generally quite small. The third category is iron losses. Iron losses, as we discussed in chapter number 2, you always have hysteresis phenomena in motors, generator, transformers, any power system which has where you have magnetism. You have the charging and discharging of dipoles, and due to those charging and discharging you have hysteresis curve and hysteresis losses. And also you have eddy current losses. Anytime you have a core where voltage is induced and current starts rotating in circular fashion, those are eddy currents. And due to eddy currents you have heating of the core, which contributes to core losses. And if you remember, to reduce eddy current we laminate the cores into small pieces. And to reduce hysteresis losses we use material for which the hysteresis curve is not too thick. It is a thin curve, so the loss due to hysteresis is small. So these are main losses in the motor. This figure shows you the categories of different losses. You have electrical losses, of course, you have core losses or iron losses, and you have brush losses. So these are your electrical losses. And then you have mechanical losses, which is windage and friction. And then if there is any other loss that you cannot put your finger on, then you put them in the category of stray losses. So conductor losses, again, those are I square R losses. So for example, if you know how much current is flowing through your armature, then the armature loss in the resistance of the armature is simply IA square RA. Likewise, if your generator or motor is shunt, then you have the shunt field resistance, and if you know the field current, then IF square RF will be the shunt field. And if you have a complex compound motor, then you have the series coils as well, which are in series with the armature or load if it is a generator. Then of course the current that is flowing through that series coil, that loss will also be considered as the conductor loss, and that loss will be the current that is flowing through that square of that current times the resistance of the series coil. There is another way to calculate the loss, copper loss, because of the weight of the conductor. And this is the equation. PC is the copper loss per kilogram. J is current density, and the unit of this current density that we take is ampere per square millimeter, ampere per millimeter square. Remember, the general unit of current density is ampere per meter square, but in this equation we are using ampere per millimeter square. Rho is the resistivity of the conductor. Again, the unit of resistivity is generally ohm meter, but in this case we are taking nano ohm meter. And D is the density, for which we are taking standard unit kilogram per cubic meter. Now, why we are taking different units? We are taking different units so that we can get a nice number over here, 1000. And in general, the current density is your basically area through which the current is flowing is usually very small, so millimeter makes more sense. And likewise, your resistivity is generally quite small in nano ohm, so nano ohm makes more sense per meter, that is. So how to calculate different quantities and which quantities you can get directly from a table. Rho is the resistivity of the material, and you can calculate rho using this formula. Rho naught is the resistivity of the same material at 0 degrees Celsius, which can be obtained from a table, as you will see. Alpha is the temperature coefficient of the resistance at 0 degrees Celsius, and T is the temperature at which you're operating the motor, which is the room temperature or ambient temperature in Celsius. So you can calculate rho using these quantities, which can be observed from a table, as you will see. So these two quantities you can observe from a table, and of course the operating temperature is given to you, or you know what operating temperature is that, and using that you can calculate rho in nano ohm meter. J is usually again obtained from the table, and D is obtained from a table. And that table that I'm referring to is in your textbook on page 918, table AX2. And I'm putting the image of that table over here as well. So observe, you have the electrical properties, mechanical properties, and thermal properties of most commonly used conductors and insulators. So the one that we use most commonly, of course, is the copper right here. So for copper, resistivity is 15.88 nano ohm meter at 0 degrees Celsius. Temperature coefficient is 4.27 into 10 to the power negative 3 at 0 degrees Celsius, and density is 8890 kilogram per meter cube, which is again a standard unit. So these are used very commonly, these quantities. So before I start the next, go over the next topic, let's look at this example 6.1, basically that relates to what we discussed regarding the conductor loss as the weight from the weight of the conductor. So a machine is rotating at this speed, armature winding has the weight of 50 kilogram. Given current density is 3 mega ampere per meter square. So remember, the one that we use in the formula is ampere per millimeter square. So we have to change this. Operating temperature is 90 Celsius, iron loss is 1 kilowatt. Calculate copper loss and mechanical drag due to iron loss. So from the table, as I mentioned, we first observed the density, which is 88.90. Let me make sure. I thought it was 8890. It's 8890. It's not 88.90. So I'll fix it. I think I used the correct value over here, 8890, but by mistake I put a 90 over here. So anyways, this is 8890, and I'm gonna go ahead and fix it, but make sure this is 8890. So 8890 kilogram per meter square, and rho naught again from the table, 15.88 nano ohm meter, and alpha, the temperature coefficient at 0 degrees Celsius, is 4.27 exponent negative 3. So from these values we calculated resistivity at 90 degrees Celsius, which is the operating temperature, and that came out to be 21.988 nano-ohm meter. Current density is given in ampere, is required in ampere per millimeter square. It is given in mega ampere per meter square. So we go ahead and change that. Mega is 1 exponent 6. So I chose this, 3 into 1 exponent 6. And 1 meter is 1000 millimeter, right? So millimeter square, or rather meter square, is 1000 millimeter times 1000 millimeter. So that's going to give you 1 exponent 6 millimeter square. So that's going to be 1 meter square. So 1 meter square is 1 exponent 6 millimeter square, and that's what we did, 1 exponent 6 millimeter square, and it will be 3 ampere per millimeter square. And we calculated the copper loss per kilogram and then multiplied that by the total weight of the copper to get the total copper losses. Calculate mechanical drag due to iron loss. So what iron loss does is basically the effect of iron loss is to produce a mechanical drag on the movement of the motor, and it is measured in the torque, in terms of torque, and it is given right here. Iron loss impose a mechanical drag on the armature, and their effect is producing mechanical friction, and it is measured in terms of torque. So basically you are calculating the torque corresponding to the iron losses in that example. And the formula of torque is this, formula of power in terms of torque is this. So you calculate torque from there. P is the iron loss, N is the rotation per minute, and from that it turns out that the mechanical drag due to the iron loss is 10.611 Newton meter, which is the torque due to the iron loss. Okay, I'm gonna go back to the topic, losses as a function of load. So when your machine is unloaded, for example your motor, if it is rotating without any load, then basically you have frictional losses, you have iron losses. Your armature current is extremely small if it's a motor, hence the armature copper losses can be neglected. Likewise, if you have shunt field, you have a constant current going into shunt, and those losses will be considered. If you have a series, if a compound motor, if you have a series field, then again armature current goes through the series, and armature current at no load is quite small, hence those series losses can be ignored. So at no load, shunt losses will be considered, and iron losses will be considered, and mechanical losses will be considered. Now once you put load on a motor, then armature current increases, and hence armature losses increases. So the heat in the armature, through the armature resistance, it increases, and those losses need to be considered. Likewise, again, if you have a compound motor, the heat generated in the series field needs to be considered. So as you put load, the other losses remain same, that is the shunt field loss remains same, frictional losses in general is considered to be same, and iron losses are considered to be same. The other losses that you have to include are the armature losses, armature resistance loss, and if it's a compound motor, then the loss in the series field. Efficiency of the machine, it is measured in terms of output over input. Output can also be measured as input minus the losses, total losses, and input can also be measured as output plus total losses. So any of these formula can be used to calculate the efficiency of the motor. Now in shunt motor, generally in chapter number 5 we did not include any losses, iron losses or frictional losses. The only losses that we considered were the copper losses in the shunt field and the armature. Now in this chapter, if a question is given to you, and of course these other losses will be given to you, there are two ways to analyze those losses. If you add up the armature current and the shunt field current. And if the sum of those two currents is not equal to the source current, then basically you go ahead and show that there is another parallel path which is comprised of the other losses, iron losses, frictional losses, and all those things. And the current that is going in these three paths will be equal to the source current. So this is one way to analyze it. Again, this is only if the source current is not equal to the armature current. This is the armature current and the field current, shunt field current. Then some current, of course, is being supplied to compensate for these losses, and we show them as a parallel path. This is there's a less trivial scenario. The more commonly used scenario is that we consider those losses as part of the armature in general. Other losses part of the armature. So in that case, basically we have a circuit. Let's say if I have the shunt motor, then we make a circuit like this. Let's say if I have a compound motor, since we have a compound motor here, I'm just going to go with compound motor. Then we make circuit like this, and then we show those losses either as a resistor or just as a box. And these are my losses due to iron and mechanical and any stray loss that you can think of. So if it is, again, this is more common scenario, this is a less common scenario. Generally, when I give you a question, I usually mention that assume those losses part of the armature. So once I mention that, make sure you keep you make another either resistor or a box and put it in series with the armature. And you will have to consider, of course, that there's a voltage drop across that. So E loss, because the voltage ES will be equal to the voltage here plus the voltage here E naught plus the voltage here EA, and if it's a compound motor, then of course plus the voltage in the series field. So these all voltages will make up ES. So what is the effect? The effect of these losses is that your E naught is going to be smaller in general, right? Your output voltage is gonna be smaller. And then E naught is the back CEMF, and if E naught is smaller in general, your output power is going to be smaller as well. Okay, example 6.2 is a shunt motor with field resistance 50 ohm, armature resistance 2 ohm, is operating at no load, speed of rotation 1000 RPM. It's a lap wound motor. Armature current is given to you, field current is given to you, frictional and windage losses are given to you, and everything pretty much is given to you. And it has been asked what is the efficiency of the motor. Once you read it, it is pretty straightforward. I don't really have to go over it. Example 6.3 is what I was mentioning. In this one, I'm basically telling you that iron losses and windage losses, frictional losses, they are 50 watt and they are part of the armature. So I'm showing them as a resistance in series with the armature, and the voltage over here, I'm assuming this is the voltage over there. So this voltage induced voltage basically is this voltage minus this voltage minus this voltage using KVL. That will be the induced voltage that I'm calculating right over here. So this voltage will be assumed, and again the effect of this voltage will be that E naught is gonna drop down. So again, go over the example, but again, if I give you that they are part of armature, then this is how you're gonna take them. Life expectancy of electrical equipment generally depends upon the life of their insulating material. And the life of the insulation material is based on what type of insulation is used. Generally, there are different types of insulation as it is shown in this table. Insulation A, E, B, F, and they are based on how much temperature they can sustain. So 105 degrees spot temperature, 120 Celsius spot temperature, and so on and so forth. So basically, if a motor has a class A winding, class A insulation, it can sustain up to 105 degrees Celsius. If you run the motor at 10 degrees Celsius above that, 115, then basically the life of the motor becomes half. Likewise, if you go double of that, 125, if you add 10 degrees Celsius, then the life expectancy is going to go half of half. So every time you add 10 Celsius, the expectancy of the electrical equipment to last becomes half. And it is given in this section, so you can read them. Again, thermal classification, I picked this table from Wikipedia. I think similar table is in your book, not as detailed, so this table is pretty good. And speed and size of a machine is based upon how fast the motor is rotating and how much power it can supply. So in general, how much torque the motor can supply. So as an example, I'm showing you two motors, 100 kilowatt running at 2000 RPM and 110 kilowatt running at 200 RPM. And they are developing same amount of torque. So they will have same size. So that means the motor that is providing low power and running at low speed, it is not very efficient as far as size is concerned, because for the same size of motor you can get higher power and it is running at high speed. So to get 10 kilowatt and to run the motor at 200 RPM, or in general to get 10 kilowatt and lower down the speed, you can use the same motor, that is the motor that can produce up to 100 kilowatt at 2000 RPM. You can use the same motor, but what you do is you use gears. You use gears to basically run the motor and run the load at the lower speed. Hence, you can use the same motor that can provide higher power and you can run it at a lower speed to get the power that you need. And this way it is much more efficient. It is much more efficient in terms of the cost of the motor, because again, this motor can serve two purposes. It can supply current at a higher speed. It can supply higher power at a higher speed. Plus, if you just add gears, you can get your required power at lower speed. But the motor with lower power, of course, it cannot supply higher power, of course, because the capacity is only 10 kilowatt, but the size is the same. So cost wise, of course, this motor is not very efficient and this motor is efficient. So it's better to use the motor that is providing higher power at higher speed, use gears and use them for lower power. And this is the end of this chapter.